All right, welcome everybody to the Yaron Brook show, and I'm excited about today's show, partially because it's about a topic I know nothing about, which is always more fun, because we've got a world-class expert here to explain it to me and to all of you at the same time. Let me just do something quick here on YouTube so I get it, because I left everything to last minute.
I was distracting you, sorry.
Hey, Dale. No, we are, yes, we're on YouTube, we're on Facebook, we're all set to go. No, I haven't gone live on Facebook. Okay, now we're live. All right, so we have Dale Stevens with us today. Dale is an associate professor at York University in what? It's not exactly neuroscience, animal behavior.
I'm a professor in the Department of Psychology.
That's right, the Department of Psychology. But what did you get your PhD in? So what is?
Well, I had a master's degree in neuroscience, and that was animal research.
Yep.
But I went on to a PhD at the University of Toronto in human neuropsychology, and really got into the field of cognitive neuroscience. So that's what I would call myself, a cognitive neuroscientist.
Cool.
But I am in the Department of Psychology in the Faculty of Health at York University in Toronto.
Good, and we'll get into what cognitive neuroscience actually is, because I'm curious.
Sure.
But I'm curious about your background. So tell us a little about where you grew up, when you discovered Ayn Rand for the first time, and to the extent to which you think Ayn Rand has had an influence on your academic career, on what you've studied and where you've landed up.
Yeah, sure. Be happy to. So I grew up in a town called Kitchener, which is in Ontario, Canada. Not too far from Toronto, actually, about an hour and a half away. And I think I always had a real strong interest in psychology. My passion was always trying to understand people, trying to understand how things work, like memory and how the mind works. I came across Objectivism through my older brother. He was 4 years older than me, and he was an engineer at university, and high-powered intellectual guy. And he discovered Objectivism and Ayn Rand through the Canadian rock band Rush.
Okay, the Rush connection. Right.
Yeah, the Rush connection. Yeah. Probably how a lot of Canadians came across it.
Well, there are a lot of Americans too. I mean, there's a vast number of a certain age, I think, a little younger than me. All the way down to around where your age, who discovered Ayn Rand through Rush, through the Anthem album.
Which, as an aside, is a fantastic and interesting point, that the power that a band and music like that can have, disparate ideas. Incredible. So
that was the power of art, right? The power of aesthetics.
Yes.
Disparate ideas, and of course we all. I mean, you're going to tell us about reading Ayn Rand, but I at least read Atlas Shrugged, which is a piece of art. But yeah, I mean, it's amazing how much even something like a song can move somebody and move them to go and think about new ideas and go read something completely different. So yeah, very exciting.
It is. It's mind blowing. So that's how Rob discovered, and he really got into reading the books, and I think he was drawn there starting by reading the Romantic Manifesto.
Oh wow!
And the ideas in art, which oddly is going to be sort of exactly the opposite of where I think I came at my interest in Objectivism. But I was introduced to the ideas through him. He started up a university club at the University of Waterloo and got connected with the Ayn Rand Institute and was supported that way. Hosted some great debates between some really high-powered people at the time. And so I started
famous 1980s debates.
I don't know if they would. I don't know of that title, but he had a debate between who was then the Premier of Ontario, which would be like a state governor, and John Ridpath.
Okay.
In front of a large audience and some other good debates.
That's great.
Anyway, and he hosted groups who listened, and so I actually joined in and listened to. The first thing I listened to was Leonard Peikoff's history philosophy lectures, and just learned a lot about philosophy. And I got really, really interested in philosophy, and what attracted me the most, I think, was the epistemology, particularly. And so, I read the novels, and that's what really did it for me. I started by reading The Fountainhead, and then Atlas Shrugged, and I couldn't put them down. And Probably hurt a year of school by staying up all night reading the books every night and not getting to class on time. But served me in the long run, I think. And when I got to university, I thought about taking philosophy. So I was taking a general arts, trying to decide what I wanted to major in. I took psychology, economics, and philosophy. And it took me one class in philosophy at my university to decide I was not taking any more philosophy at post-secondary institution anyway.
Yeah.
It was a terrible experience.
Yep.
But psychology was amazing. Like my first class was by a guy named Peter Fried, and I'd go to these lectures at night with 300 people, and it was like going to see a live show every week. It just
Oh, wow.
it was fascinating. I loved it. I was engaged in the ideas, but I continued to study philosophy on my own on the side, and particularly studied Objectivism through the Objectivist Academic Center.
So which years were you in the Objectivist Academic Center?
I was in several incarnations of it over the years. So probably through the years, late 90s to early 2000s.
Okay.
To mid 2000s. So I was in a Bachelor of Arts, undergraduate in psychology. I found myself constantly drawn more towards the biological side of psychology, partially out of frustration with some of the other fields. And not feeling like they were really grounded in science, and the theories weren't well defined, and the field was what I would feel more like a proto field, than a coherent scientific field. But I did like the biological psychiatry and studying really the brain and the mind. So by the end of that, I ended up working in a lab, working with animals and studying some memory and behavior in animals based on different kinds of disease models. And I did my first graduate degree this is at Carleton University in Ottawa. So I did an undergraduate, and then I did a 2-year master neuroscience degree, and that was with animals. And he studied all kinds of things. And so I got a real love and passion for experimental research and the science and the scientific method. And kind of came to a fork in the road where I thought, do I want to be a clinician? Do I want to go into med school, be a neurologist, be a neurosurgeon, or if I could get there. And to me, I think those are noble professions and wonderful. And for me, it was really the discovery aspect. So doing science and doing experimental research always felt like being an inventor and explorer kind of mixed into one. It's long delay of gratification, a lot of hours, but to discover something that is not yet known, it's pretty exciting. So, but I realized after, 2 years of counting cells in a microscope that I'd gotten pretty far away, rat retinas, that I'd gotten really far away from the human mind. So I went and did a PhD in human neuropsychology at University of Toronto. And I was actually trained clinically there as a clinical neuropsychologist.
Okay.
But the program is primarily research-based, but I did extra curriculum some of that was working with in Practica with patients with closed head injury, stroke, traumatic brain injury, neurodegenerative diseases, things like that.
Yeah.
And at the end of that, I came to another road. I had to decide, do I want to be a clinical neuropsychologist and work with patients and work in an applied field? But again, it was really the fundamental research I was interested in. So I got an opportunity to go work with a guy named Dan Schachter, who's a very well-known, famous memory researcher at Harvard University. And my work during my PhD was really focused on memory, higher level cognitive functioning, with a real strong interest in aging and the changing brain across the lifespan. What kinds of things change, what doesn't, what defines typical healthy aging versus pathological aging.
Yeah.
But really more about the way that across the lifespan, the way we think, the way cognition works changes pretty typically across people, even healthy aging individuals.
What's the primary way in which you study that?
Really working with, I start by working with experiments where we're targeting certain aspects of memory or certain aspects of cognition and working with older adults. So, I spend a lot of time working with healthy older adults who are willing to devote their time to come in and participate in research. And my main method has been using neuroimaging. So MRI, magnetic resonance imaging.
Yeah.
And my expertise was in functional magnetic resonance imaging, which is the ability to, we use a particular kind of technique to get a measure of ongoing brain activity, sort of in real time in the brain.
So how do you correlate that, for example, with, I don't know, with healthy memory loss as you age, or unhealthy memory loss as you age? I mean, I can see people doing like tests and stuff and measuring, but how do you correlate that with then brain activity?
Yeah, well, I mean, the way it works is that with the functional MRI scanner, the MRI scanner, you're reading something that is actually it's related to blood flow, or related to the amount of oxygen in the brain. And so, the brain will actually, when the neurons become active, they start to use up oxygen and energy. But the brain is extremely efficient at, all of a sudden, rapidly increasing blood flow to that region. And so when that happens, that's something we can detect with our MRI scanner in very high resolution, right through the brain and all 3 dimensions, pretty high resolution. And so we can get an idea of how much different parts of the brain are active, or even more than that, we can actually get an idea of how much different brain regions are communicating with one another. And so essentially, one of the main ways to do this is to run cognitive experiments where we're studying the effects of aging, or looking at correlations of changes in brain activity that have an impact on behavior.
Okay.
So it is primarily, so we do run well-controlled, experimental research. But when we're looking at the brain activity, we're always working at a correlational level. We're correlating the patterns we see with, the manipulation of behavior or the expression of behavior in the scanner.
Okay. And how similarly to human beings does the brain, does what you see in the MRI scans of the brain look similar across human beings, across, let's say, normal, not who don't have a pathology?
Yeah, so that's a really good question, and I can come up with, I think there's some really fun examples.
Yeah.
Because that's a relative question. You could say, no, the whole importance of what we're doing is trying to study individual differences, and there's radical differences across different brains, and on some level that's true. But some of the techniques that are coming out now, there's been some really radical advances lately in the way we're using functional MRI, and the way we're analyzing it. So, rather than just sort of looking at, does a piece of the brain become more active or less active? We're able to sort of model, what's happening at a neuron, or not at the neural level, but at the level of interaction of networks. So I'll give you an example of a really cool study that came out. Wasn't by me, but a group published a study in the journal Nature Neuroscience. And if you'll indulge me, I'll just tell the story because it gives an example of how incredible the technology has gotten. They had a large group of, healthy young adults, probably college students, who came in, they lay in the MRI scanner, and they showed them 20 minutes of a TV show. And in this case, they were showing them an episode of Sherlock, the BBC series.
Yeah.
Right? And so they had them watch this, about 20 minutes of the show, and they're scanning the brain. At the end of that clip, at the end of the 20 minutes of the show, they said, okay, now I want you to just verbally recount the entire episode. Right. So they would do this, and this is the best they could remember. And one of the cool things about TV shows like this is it's broken up into epochs. Right. Yep. So there are scenes, and there's a cut, and there's a different scene. Yep. And, we have a way of unitizing that in the brain as separate events. And so they did this with, a large group of people. Well, one of the cool things is that they replicated some previously research that's very interesting, where by using some machine learning algorithms and some things called multivoxel pattern analysis, they're just some more recent, little more advanced analysis techniques. By sort of training their algorithm, they could now feed it brain activity, and you can tell what part of the movie they were in by looking at the brain activity.
Okay.
Right. So you could say, what point in time when the brain looked like this were they looking at? And this thing can tell you, well, they're at this point in the movie. Well, that's cool. And people have done that before. That was a big advance, in the way it looks like we're edging towards mind reading. Right? Well, what they did in this study that was fantastic was they could take one person's brain images, and once they trained this algorithm, and feed in one person's brain images, and then be able to tell by looking at another person's brain activity what they were watching. So in other words, you're decoding what the brain, what somebody is watching on TV, looking at their brain activity by having learned it on someone else's brain activity. Does that make sense?
Yeah. So that implies that there's a huge amount of similarity between how we analyze information, or how the information is it's what's the best way, consumed by our brain.
Yeah. How it's processed, and
How it's processed.
and you know and you know we have a good idea about what a lot of these various different sort of brain systems are doing. So that was fascinating. What they went one further and showed that, in fact, and this is where it got interesting, by looking at the brain activity when somebody is watching the show, they could predict from this brain activity while they're narrating the story what part they were narrating. So in other words, the brain of a single individual is highly similar when they're watching the movie as to when they're later recounting it.
Recreating.
So in one sense, you know, part of remembering or imagining or reliving something is to reactivate those regions that were, you know, active at the time of encounter and encoding. And they finally went one further, and they could do that across people. So you could look at brain activity of one person recounting the episode,
yep,
brain activity of another person watching it, and match up which part of the thing they were in. So, you know, we think of ourselves as being radically different from one another and individuals, and I think that's true. But in the fundamental way the brain is organized, yeah, and the systems and the processes that are there are remarkably similar, and that's something that I study in particular. That's very interesting to me.
So, so tell me a little bit about how you would define what neuroscience is and what it studies, and what in particular cognitive neuroscience is.
Okay, sure, I can do that. So neuroscience is pretty broad. I mean, and it covers everything. It's any study of the nervous system, and that's either central or peripheral. So you can be looking at paralysis, regeneration of cells in the spine after spinal damage, to really basic neuroscience, trying to understand the basic mechanisms of cell membranes and in other species like aplasia and very simple neural organisms. Yep. Right up to trying to decode brain activity, and then to go beyond, even modulate brain activity. So cognitive neuroscience is one branch of neuroscience, and there are various definitions, but I think a good one is it's a branch of neuroscience concerned with the biological processes of the nervous system, which forms the basis of cognitive functioning. Simply, if you ask somebody, there's I think the person who is sort of considered to be the founding father of cognitive neuroscience would be a guy named Michael Gazzaniga, okay, who's still around and gave a really good talk at the Cognitive Neuroscience Society recently. And he defines cognitive neuroscience as the study of how the brain enables the mind.
Okay,
that's what he says.
Cool. Yeah.
But I did once use that definition and have Harry Binswanger tell me they didn't think that was actually a definition. He might be right. Yeah. But what I look at, the
definition you gave originally?
No, the one that I read from Mike Gazzaniga.
Okay.
But really, I think it's really about studying the nature of the mind-brain relationship. Yep. And so, and if you think about, where it came from, what cognitive neuroscience as a field grew out of, for a long time, we've had cognitive scientists, and they study the mind and cognition and the way we think through just experimental testing, behavioral testing, right? Yep. Or psychophysics, right? So flashing beeps and dots or pictures and measuring reaction times and testing memory, things like that. Yep. There's a huge, long, incredible tradition in cognitive science. And another field that would be sort of the other founding field or previous field would be, I would think, neuropsychology. And so really that tradition came from the study of patients, people with brain damage. And that really exploded probably sometime around between or towards the Second World War, around those wars, when for the first time in history, there was a tragic, but really, easy access to a lot of people with a lot of brain damage. Sure. With the kinds of warfare that was going on at the time. Some of that continuing now. But a guy named Luria,
So suddenly they discovered that it damaging a certain part of the brain affects our particular skills or particular abilities.
Yeah, I think, and that's really when things exploded in our understanding of the brain. You can look at the history of it and when it was considered to be just a cooling system for the heart and the blood, all the way to, the marrow of the skull. The Egyptians didn't save it when they mummified bodies. They threw it away, Okay. They saved the organs and sucked out the brain and threw it away because it was just marrow of the skull. Yep. But I think, things came a long way. But around that time, they started to understand that, wow, you could get fairly specific kinds of deficits and quite consistently across individuals with damage to fairly specific parts of the brain, right? So to concretize that with some examples, one of the first ones is a guy named Paul Broca, who realized that if you had some damage right up about here in the frontal lobe, just on the side there, you could wind up with something that we still refer to as Broca's aphasia. So perfectly fine ability to comprehend language, but an inability to output, to speak it. And so it's extremely difficult. Now, there are a lot more subtleties to what that deficit's actually about, but that's one way to think about it, language production deficit. Very shortly after, and he found this in a number of patients. He had a very famous patient called Tan who could say nothing but Tan, and Tan's brain is preserved in a jar in a museum somewhere. Okay. But he found a number of patients with this very similar damage that had that very specific deficit.
And they could write.
They can read, they can write, they can
think.
They seem to be fine. Yep. Now, more modern analysis reveals that it may not be that simple.
Okay.
That's probably a little beyond the scope here, but very shortly after that, a guy named Wernicke discovered that, wow, there's another spot back here. Same side, both on the left, a little bit over the ear, sort of in the temporal lobe here, where you get damage there and people lose language comprehension. Oddly, they seem to have fluent, normal sounding language output. Of course, it's not normal. It doesn't make any sense. It's a word salad. Yep. But it's not halted, stilted. They can't form the words. They can babble, and with intonation, and so this is where they started to say, "Wow, there's these little patches of cortex that are responsible for different things." And so, to maybe exaggerate a little bit, I think where cognitive neuroscience really started, and when we started to get these incredible tools, these neuroimaging tools, the place where it would come from was one of a perspective on the brain that's very modular. And so there's kind of been a really big ongoing tension in the field of psychology and field of cognitive neuroscience forever between this modular or localist kind of view, where you've got little bits of brain that are specialized for certain kinds of tasks or certain kinds of content or domains. Right? Mm-hmm. On the flip side, you've got sort of a distributed, or maybe people call a holism or distributed view. On the extreme side of that, it's all equipotential. Any part of the brain can do anything. It'll specialize and things can take each other up. Yep. But I think the way it's looked at more now is we're starting to realize that, we all take for granted that the brain is a network. We know that it's a big, complicated network of neurons and, structures. But we haven't really looked at it that way or treated it that way for a long time when we got these neuroimaging tools. So around the time that we had positron emission or PET scanning, which is the first time they could actually look at the brain and see things light up when people were doing things, to MRI. The gold standard was always sort of, okay, that's fine. It's a correlational measure. But the gold standard is if you can find a patient who's got damage limited to a particular structure in the brain, showing a particular kind of a deficit, now we can say something causal about that brain region.
Yep.
And so I think there was a history of coming from a very modular view, but I would like to think that if there's a pendulum swinging, it's going much more towards looking at the brain as a network.
So if we look at the brain as a network, does that mean that if you lose that capacity from that one region of the brain, then you can relearn it because the rest of the brain can somehow compensate for the damage done there?
Well, yes and no. So we do now realize there is an incredible amount of literally even rewiring, but definitely functional compensation. Sometimes even just, you say functional compensation, that could mean the brain does things different ways, or that people achieve tasks learning through different means.
Yep.
Now, that's not to say that there aren't, that those bits of brain, well, I guess what I would argue is if a module means that it's a patch of cortex that does a particular process or prefers or treats a particular kind of content, I would say that's probably not the case. Now, that's not to say that parts of the brain aren't specialized for certain functions and that some damage is going to be catastrophic and can't be, you can't recover from some kinds of brain damage. Yeah.
So what are you focusing your research on now?
Yeah, okay. Well, that's a fun place to go. And what I could maybe I'll pick up with sort of my narrative of where I traveled around to, because that sort of brought me to what I'm doing now. So after I'd finished my PhD, I got to go down to Boston and live there, work at Harvard for about 5 years, which was a great experience. studying memory. Now, at that time, I was always kind of, I think that I was sort of at the limits of what my advisor, my supervisor, Dan Schechter, would consider under the umbrella of memory research and what he was interested in.
Okay.
It's very related, but I was really keen on trying to get an understanding of what concepts are about. Informed by what I found to be the most fascinating read I ever read, which was Ayn Rand's Introduction to Objectivist Epistemology.
Yep.
And so that fascinated me, and I realized that there were all kinds of links to memory and the way memory works.
Okay.
So I studied that, and I honed skills, and I worked with I got a lot of training from working with some of the best people there at Harvard.
So tell us a little bit about that. Tell us a little bit about the connection between concept formation and memory, and then how you study concepts. What does that mean to study concept from a neuroscientist perspective?
Well, yeah, okay. I would say that, I mean, I'm sort of working towards that. So I'm going to acknowledge that this is a journey, and sort of my end goal was to stay in this field so that someday I could bring that really back together with my understanding and passion for the ideas of Ayn Rand in terms of epistemology and her theory of concepts, and really study that. But I'm somewhere along the way. And part of that is that, when you're coming up in your training, you're partially independent, but you're always working for someone else. Yep. And I had some of the best in the world, working for Dan Schechter. I moved on to the National Institute of Mental Health, which is in Bethesda, Maryland, just outside DC. Yep. So that's the federal research, intramural federal research facility. Yep. And I worked with a guy named Alex Martin. Now he's kind of a giant in his field, and is one of the guys who's been for a long time looking at concepts, but in terms of what he would say are object concepts. So abstraction, but kind of first level abstraction. Okay. So moving from Harvard to working with Dan Schechter to moving with Alex Martin gave me the ability to really start working on something we could call concepts. And so I can talk about and circle back and say how that all kind of fit together.
So say something about memory and memory and the relationship with memory to concepts, and how what are you looking at as a neuroscientist when looking at those two? And then those first level concepts, that's really interesting. How do you, again, what do you do as a neuroscientist to study first level concepts?
So first with memory, it occurred to me, and this is something I'm still working on, so I'm going to feel free to kind of put out new ideas that aren't worked out necessarily and published. But to me, the idea of memory is you're able to have we all know in general what we mean we say memory, but it can mean a lot of different things, right? So memory can be what did you have for lunch today? If you stop and think about it, you can probably remember. Sure. If I say what did you have for dinner last Sunday, you might be able to take some time and bring it up, or you might not. But that's one kind of memory, right? And we think of that as kind of mental time travel. Are you able to actually go back and bring up that information? And when you do get a piece of it, you sort of brings the other pieces of information online, right? The context. You might pretty quickly remember that, well, you're having dinner with somebody, and it was at a restaurant, and that it might have been raining outside on the way in, and the whole thing came back. That's reliving it. On the other hand, I can ask you something like, what's the name of the street you grew up on? You could probably remember that, or the name of the school. Yeah. Now that's a memory that'd be an item of fact. Now, if I were to ask you, when did you learn that? Is it associated with a particular time and place? Yeah. You'd probably say no. It's knowledge, right? Well, in a sense, knowledge is memory too, right? We have a store of memories that are now abstracted away from the original experience, and they exist as concepts and knowledge. And so, what occurred to me is that a lot of what we talk about when we're talking about memory is really just abstraction across time. So, what is the common denominator, and what are we abstracting across? And that is time. And that in many sense, all of what we can do with memory is based with human memory, and what we think of as memory that's probably unique to humans, is based on the idea that we have a conceptual faculty. Now, in terms of talking about first level concepts, that's
so you say that only humans have memory. Is that true?
No. Now, again, memory. The term memory refers to lots of phenomena that are related. Now, you can talk about working memory. If I give you the digits 73256 and ask you to go write them on a piece of paper, sure, you're probably going to rehearse that until you find a piece of paper and write it down. We would call that working memory.
Okay.
right? That's actively maintaining information in mind.
Yep.
Why would you call it memory? Well, you're holding it in your mind while it's no longer perceptually in front of you, right?
Okay. Okay.
Now, and I've had debates with other neuroscientists and psychologists and even other objectivists about what constitutes memory. But in general, we talk about different kinds of memory. And so clearly, if you're talking about learned associations, if you touch an acidic environment, curl up, low-level slugs will do that. So all kinds of organisms have memory on some scale, depending on what you're going to include in the umbrella.
Sure.
But if we're talking about, consciously reliving experience, I think that, Ayn Rand would say in ITOE, an Introduction to Objectivist Epistemology, as would, most psychologists, there's a uniquely human kind of memory, and that's the ability to consciously re-experience the past, or even do so volitionally, right?
Yep.
Where you choose to recall an event, or somebody asks you a question, and you can turn your mind's eye inward, introspect, and recall memory.
Yeah. Yeah. That's a fading skill for me these days, but anyway.
Don't feel bad. It's fading for probably everybody listening to this.
Yep.
Starts earlier than you'd think.
Yeah.
That's an interesting point that Yaron. I would put out there that although certain aspects of memory do decline just quite consistently in typical healthy aging,
Yep.
there are aspects of memory and of cognition that, barring a pathological condition or a neurodegenerative disease, don't decline in typical healthy aging.
Yeah.
In fact, can improve across the entire lifespan. And that's some of the important stuff. That's, again, what we would call semantic memory, which is just, or some people will point out that it's verbal memory or verbal intelligence. But what it relates to is the buildup of crystallized knowledge, which means facts of the world, facts and knowledge. That's not something that just declines unless you've got some sort of a pathological process.
I was at dinner the other night with this woman who's 98 years old, and she was as sharp as anybody I know. Yep. And she was telling stories from the 1970s, and I mean, her memory was crystal clear. I mean, it was pretty amazing.
Oh, it's incredible. I mean, I had an experience where, I was lucky enough to have some of my grandmas and even great grandmothers around in my lifetime. And not that long ago, before my grandmother and my wife's grandmother had passed away, I had the occasion to play Scrabble with both of them, and just got, creamed, like really got beat. And now one thing, they've been playing Scrabble a lot longer.
Yeah.
But my grandmother, I don't think went, even to the end of high school.
Yeah.
But nevertheless, verbal knowledge, build up of knowledge and facts, and it happens across the lifespan. So
we have a question here.
Sure.
Is it true a person can be tricked into having a false memory?
Yeah, that's true. So, I mean, there's quite a bit of research to back that. It's an interesting question because the guy who I worked for, Dan Schachter, one of the things that he is quite famous for, as anyone, is understanding false memory.
Okay.
And memory errors. So he has a couple of books that are available in almost any bookstore. One of them was called The 7 Sins of Memory, where he really breaks down, the various ways that memory can go wrong. And I mean, there's another woman named Elizabeth Loftus who worked with him. There was an incredible amount of controversy around that because there was a time where, there was a sort of a battle raging among the scientists and in the courts, and politically about recovered memories.
Yep.
Or, that were repressed memories that people were, either actually or, falsely recalling during therapy sessions. And, there were, people, there were court cases and legal trials. And there were other instances of towns being completely turned upside down by reports of satanic rituals and twisted things going on that the children had reported.
Yeah.
And some of them turned out to be completely baseless. And in hindsight, we understand that had a lot to do with a lack of knowledge about how you can, what the state of the mind is of a child that age and that development, how the way you ask them questions and approach that can change their memory. But there's some really pretty striking examples of studies out in the literature where you can, quite a few people will report remembering something that they've been told. And it's interesting. I think I think that it doesn't damn memory as an unreliable, or doesn't, I don't think it damns us to subjectivism. I think it comes back to the idea that we are objective, that we don't digitally take in, record digitally exactly what we, moment to moment perceive, that the information we take in, what that means, what we take in has to do with what we focus on in a given context. The way that it's stored and the way that it's recalled is structured in a way that is adaptive for human existence. And that's not to have a second by second digital replay of everything that happened.
Yep.
And so back to Dan Schachter's 7 Sins of Memory, one of the things he's famous for pointing out is that the way that our memory can go wrong, the various ways that our memory can fail us are very, give us a lot of insight into how the memory system works.
Okay.
Why it evolved the way it did. So.
And is it, so some people like my wife remember everything, right? I mean, I remember from age 3, they remember a huge amount of information. I remember almost nothing. I mean, literally, life started about 10 years ago, because before that, I don't remember that much. But I know people, people seem to be divided that way, that there's some people just remember a huge amount, and there are other people remember very little, people are somewhere in between. But does that have to do with the structure of the brain? Does that have to do with a conscious orientation around memory? Do you have an idea of what is the causal factor there?
Yeah, and it's yes and yes again. So yeah, there are a bunch of factors. It's definitely the case that the individual variability in memory capability is quite striking. There's a lot of individual variability, and you'll find that even when you're running studies with just typical healthy young adults who's supposed to all have great memory, that there's a huge variance. And then there are tons of factors. Some of it's probably genetic, and some has to do with just the nature or the structure of the brain. A lot of it has to do with experience, but there are all kinds of factors. It's a very complicated equation. Things like, values, your values and your orientation will have a huge impact on the kinds of things you remember, and even just the amount you might remember. And we do have examples of people who have a disorder where they almost quite literally remember everything, the quote unquote photographically.
Yeah. And
you can go on YouTube and see some incredible examples. There's one man has an incredible spatial memory. I believe that he has autism, and he's extremely skilled in memory. So there's an example, they can fly him up in a helicopter, and I think they flew him over, it might've been Manhattan, but it was a very large city, just in a helicopter tour.
Yeah. And
he could get down, he could draw it. And I mean, every building, details in the building, most of what he saw.
Yeah.
But that's a rare, and that's, it wouldn't be an enjoyable life to have that kind of intrusive memory, but there's a lot. And I think a lot of it has to do with other factors, your personality, your orientation, what you attend to. A lot of people don't remember things because they weren't in an environment that was a happy one, and they don't.
It strikes me that it does have a lot to do with values, because I don't know. So I had a fine childhood, but I don't remember any of it. So I assume it was fine, because there's no reason to think otherwise. But it does strike me as values. There's some people that seem oriented towards the past, and some people oriented towards the future in terms of their values. Some people like to really dwell on the past, and some people who don't. And it strikes me that that's correlated somewhat with memory, because if you dwell in the past, you're exercising that muscle in a sense of remembering.
That may be, but this is well, I don't know. There's a lot you get into there, but it does segue really nicely into something that I want to say, and that is,
Sure.
I think one of the biggest advances, or what's been an exciting advance in the field, probably over the last since around the time I started at Harvard, actually, and a lot of it was going on in my lab with Dan Schachter, by some of my colleagues, Donna Addis and Nathan Sprang, and some other colleagues. And that was the idea that, again, with neuroimaging, people started to say, hey, there's these really interesting brain systems. We have a good idea about, what part of the brain lights up when we're doing autobiographical memory, say, you put somebody in an MRI scanner and you ask them to try and relive in as much detail as they can a wedding they were at within the last 10 years or something. Now we can ask people to really, truly try to imagine something in the future. like, what do you think it will be like at, your parents' funeral, or maybe something less morose?
Yeah.
And what's incredible is that, on a sort of very general level, looking at the brain systems that seem to be heavily involved, they're almost completely overlapping. And that was an exciting finding. That came on the heels of some really well-known but fascinating things of working, again, from the neuropsychology, working with these sort of famous patients who are really densely amnesic. Mm-hmm. Patients like HM, who's a very famous patient who had a bilateral medial temporal lobectomy. They removed part of the brain. And that's when they discovered how critical these were for memory. So this is a person who's sort of, when I say an amnesic, they live sort of moment to moment, always anew. They don't form new memories. Yep. They've usually lost all memory for a long period back in their life. Some people for their entire life. Wow. Some people retain memories that start only about 20 years back and go backwards from there. But the famous patient KC, and the very famous psychologist named Nendel Talving, who worked with him here in Toronto years ago, was asking him, KC, who's this, you could come in and you could introduce yourself, sit down, do some pen and paper, tests, and he's very pleasant, and you could leave, come back in, and you'd have to reintroduce yourself, shake his hand. Really wouldn't know you. Yeah. But, when he was asked, what's it like? What are you going to do tomorrow? He would say, I don't know. He'd give a simple answer like, I'll probably, type on my thing, or, do something. Yeah. So, well, no, think about it. Like, what plan out your day. What's it look like? And he said, nothing. There's a famous quote, which I won't recount verbatim, but he sort of said, what does it feel like when you try to just imagine your day tomorrow, plan out what you're going to do? Like, you're in the room, the kinds of things you do. And he says, it's just empty. It's blank. It's a void, Yeah. And so it makes sense. It doesn't seem shocking in hindsight. Well, what is memory for? Just for us, like you said, ruminate and muse about the past. No, it's to inform our behavior. It's to learn. It's to rely on that information to guide our plans and our goals going forward, right?
Yeah. No, that's it. So you look, when you do the brain imaging, so you ask people to recall particular types of memory, and then you look at what part of the brain is being stimulated. What do you, is that kind of those kind of the relationships you're looking at?
Yeah, early studies, you could do things like, people were really just saying, let's get somebody into this scanner and get them doing, recalling some memories from the past. And in another condition, they're, doing something simple like counting. And now we're going to say, the brain lights up and, lights up. I'm going to use that term. That's kind of a silly term to say that parts of the brain become active by our indirect measure. And we get some sense that, wow, at first that was exciting. It's these brain regions that we know from lesions and from brain damage, or from these surgery, these patients who've had surgery. Sure enough, the right ones are becoming active. So, but fast forward to now, and we're doing things like, using machine learning algorithms to try and look at brain activity and predict what they're remembering from a range of options, say.
Oh, wow.
And so, we're down that path. There are, to get silly, there are companies now, private companies, who say that they can do lie detection with really high reliability. And that's probably not true yet. I don't think the science is quite there. But there's all kinds of things you can do and understand about how memory works, and understand, what goes wrong. But eventually, I guess something I would mention is that this is, so far I've just been talking about, looking at neuroimaging and, looking at brain activity and correlating it with behavior. There's all kinds of other cool tools, available to cognitive neuroscientists as well. And that would maybe take me to my current job. So I'd done, 5 years at Harvard, and I did 3 years working with Alex Martin outside of DC, starting to study concepts, and we can circle back to that. When I came to York and started my lab here, I was kind of in a position to say, what is my direction going to be? If I'm going to go and, start my own shop, have my own lab and be independent and, not have anybody else to rely on, what am I doing? And I got really interested in another technology, and that's just different methods of non-invasive brain stimulation. So for example, one we would call transcranial magnetic stimulation. Okay, so that's simply, it's a coil that you hold just on the surface of the skull, on perfectly healthy, happy person sitting in a chair. And it works through creating a magnetic field. The it's a pretty specialized system, but it's not, a radically new invention. It's basically electricity and magnetic fields. But the technology they have, you can fairly specifically affect the cortical activity just on the cortical surface below the skull. So the magnetic field passes through the skull and it has an effect on the neurons underneath. And so now I think there's been some recent radical developments in that technology. So initially, I think people used it and it still went along with the idea of let's kind of sort of map out the brain into all the various modules and say, what is the causal role of this little patch of tissue? Yeah. Now that may be a bit of a straw man, but that's kind of the idea. So they would say that you could create like a virtual lesion, right? So with just several milliseconds or even up to, several seconds, I could deliver this stimulation and kind of knock out a brain region. And now we can say, okay, how does that affect their behavior? Is this brain region necessary or critical for that kind of behavior?
Yeah.
You could also do things like, show somebody something on a screen and then stimulate different parts of the brain and say, okay, exactly how fast does that information travel from the eyes to the visual cortex at the very back and on up to different parts of the brain, so you can map that out. Now you can do some pretty incredible things with TMS. That's the stimulation where you can, with 40 seconds, 60 seconds of stimulation to a part of brain region, you can have a lasting modulation of whole brain systems.
What is that?
So let me try and not go too technical. Well, the way that I study the brain now is, and always have, is very much from a network perspective. So getting away from the idea that we're trying to map out the various little bits of cortex that do different little things. It's really understanding that the brain has it's a big, very complex network, but which is sort of composed of subsystems, right? So you can say we know that there's a particular group of brain regions that are critical for orienting your attention intentionally. So we have the ability to sort of take the reins and focus on the external world and direct our eyes, but not only our eyes, our focus on what we want, or even our ears, right? Yep. So you can stand still and you can, it's the idea of be at a cocktail party. If you hear a voice you recognize, you can tune in and listen to that conversation, at the expense of hearing what else is going on. So, so we know lots about the different systems of the brain. There's a visual system. There are systems that are critical for memory, for recalling memory. There are broader systems that are critical for controlling the other systems that allow you to switch your focus from introspecting into your own mind and trying to remember something to, paying attention to the world and bringing that information to bear on the world around you. So the idea here is that this is sort of these systems or networks or subnetworks are made up of lots of brain regions that are distributed around the brain. But using TMS, if we can find one of these critical nodes or localize this thing in an individual and stimulate it in a certain way, we can actually modulate activity across whole brain systems. So now this it's early days, but it takes us from working in a sort of a realm where we're just correlating what we see with with our experimental manipulations, actually modulating activity and seeing how that affects behavior performance. The exciting thing is it might hold the promise, or there's some evidence that it does hold the promise for enhancing cognitive performance, or even improving, memory or declining cognition in someone who has a disorder who is aging. So we call that a neurointervention is what we call that. Sorry?
So it has a permanent effect.
Yeah, well, it has at least substantially long lasting effects. It can have. Okay. Now, usually when we bring people in for a study and we're doing TMS, we're doing, stimulation in the range of what we say is not going to have lasting effects.
Yep.
So it's non-invasive.
Yep.
Clearly at some point though, we know from repeated sessions of this, you can have very long lasting effects.
Okay.
So for example, the technique has now been approved in the US by the FDA for treatment of depression.
Okay, interesting.
They're having some pretty incredible effects. So
what do you think is going on?
In terms of this,
so why it has this effect and why it has a lasting effect? What is it doing?
Well, can I explain this without getting too technical? I think I can. I'll use one example. I'll use the depression example.
Yep.
Okay, so there's a one model of depression I think that was pretty well substantiated in a really interesting way of looking at it. Starting with work by someone named Helen Mayberg, who used to be in Toronto. The idea that, depression there can be several causes, right? We can think of depression as being a neurochemical imbalance, right? Where maybe it's genetic, or maybe someone's, it could be hormonal, nutritional, whatever causes, someone doesn't have enough of the right kind of neurotransmitter. These are, neurochemicals in the brain. And so that results in depression. And what you wind up with is people are unhappy. You ruminate, you focus on it. It can dominate your cognition. Your memory is poor, your attention's poor, and you're, miserable.
Yep.
On the other hand, others would argue that, depression can be from bad cognition, one might argue that it's from bad values, from bad philosophy. Or, they're just over propensity to ruminate and focus again on the past, or to revisit what's already happened and stew about the past.
Yep.
And you think about one as being sort of a higher cognitive source. And again, I'm a bit of a false dichotomy, as we'll see, but it's sort of being the higher cognitive region sort of up here in the prefrontal cortex, right? So lateral prefrontal cortex versus some of these sort of core, very deep limbic, or whatever we think of as emotional centers in the brain. So there's a region called the subgenual cingulate 25. It's sort of a little candidate area that's been a hotspot for a long time in depression research, as being at the heart of sort of where you see neurochemical imbalance.
Okay.
And so the idea would be that, well, with antidepressant drugs, you can attack it at the source, and you can, it's really kind of a sledgehammer approach, right? If you can get this thing across the blood-brain barrier, get it throughout the brain, it's going to, raise these neurochemical levels. And of course, there's all kinds of evidence that can improve people's, state in terms of depression. On the other hand, once there's some techniques, and I'm not a clinical psychologist, you have to go back and talk to Gina Gorlin or others, but certain kinds of therapy have been pretty successful with depression, like CBT, cognitive behavioral therapy.
Yep.
Some would argue that that's not the right approach, and some of the studies would argue that, in one, you're sort of acting on top down, and you're getting people to use their cognitive control in a different way to learn new habits and not focus. And from the other side, you can say, well, we can see changes in the neurotransmitters, and that propagates. Well, I think what we have to acknowledge, and what everybody knows in some level, is that those things are interacting with one another. Our focus, our values, our focus, our thoughts do have an effect on the neurochemistry and probably the functional connectivity of the brain, and vice versa. And so, there was, there's been therapy, and there've been drug interventions for people who have tried many drugs and are really, really resistant. They started to try something called deep brain stimulation. And that's actually a very invasive surgery where you're putting electrodes deep into the brain.
Okay.
Right? I mean, it's been very effective with Parkinson's disease.
Mm-hmm.
We tried that with depression. My understanding is it never worked very well. But the one sort of final move, and sort of still the gold standard in treatment, is, believe it or not, still electroconvulsive shock therapy.
Yeah.
Which is much less gruesome, but pretty much what you saw in One Flew Over the Cuckoo's Nest, right?
Yep.
Electrode here and here. It's kind of like the Windows reboot, right? You shock the brain, you induce a seizure.
Yeah.
People go unconscious for some period of time when they come around. I don't know if there's anybody has proposed a theory as to, I'm sure they have, but I don't think it's settled as to what exactly happens, why that helps. It does help a lot of people really relieve the depression. I think it's reserved for people who are really depressed, intractably depressed, and they're not responding to 5 or more medications.
Yep. The
exciting thing is that this is the roundabout way to get back to what do I think is going on? Well, now I think what we're doing with TMS and non-invasive brain stimulation is getting at the same mechanism as, we can think of it as both sort of a therapy or a drug treatment, or maybe even ECT, with a much more targeted and much less invasive kind of a procedure. So for example, ECT, they no longer strap you down and you go into a grand mal seizure. It's much more muted, but it's the same kind of thing. But people also suffer from memory loss, tension problems, and God knows what else happens. So there are some negative symptoms. So this really takes me to something that I thought might be too technical to get into, and you stop me if it is. But something that I was really interested in from the time that I started doing research at Harvard, and it was the beginning, was this idea of resting state networks. So there's been this kind of, I wouldn't say a revolution, but a whole explosion of studies in cognitive neuroscience where people still run experiments very intricately designed behavioral experiments and look at brain activity. That's important.
Yep.
But there's another additional field where you just have somebody go into a scanner, an MRI scanner, and lie nice and still and do nothing. Well, what we would call nothing, or don't give them any instructions.
Yep.
And we just look at the brain and we literally say, okay, what is the activity level of the neurons across the whole brain? And we'll scan them for 10, 20 minutes. And what you find is that we've always known is that there's all kinds of random fluctuations of the signal. It's up and down, really large amplitude. We always figured it was just noise. And so, we do these highly controlled experiments and we elicit these little evoked responses that are kind of little smaller waves on these carrier waves and ignore the rest as noise statistically to see what we wanted to look at. But it turns out that there's all kinds of incredible signal in that spontaneous fluctuation. Yeah. And what this guy named Bharat Biswal in 1995 was, he said, what's going on there? He just looked at he looked at a spot in the brain where we do know there's a part of the brain that does a specific thing. And this part of the brain right about here controls your hand on the other side. Yep. And so it's something called the homunculus. Along one strip of the brain, there's kind of like a topographical layout of the whole body. And if you poke that spot, it'll move a different part of the body. Okay. It's basically the same in everybody's brain. There's a strip of the brain just behind that. If you poke it, then they'll have a sensation in that part of the body. But that's something we get into. Yeah. Well, he looked at this fluctuating activity in that part of the motor system that controls the hand. And then he said, what does it look like? What is that? He called that a time course, right? Fluctuating. Turns out that random sort of what they thought was random spontaneous fluctuations of activity was highly correlated in that spot with sort of the rest of the motor system in the brain. So in the other side of the brain, so if you look at one spot on the side of the brain, you look at the exact same spot in the other hemisphere, that information tends to be correlated. So something's going on. And of course, as cognitive neuroscientists might have said, well, they weren't doing anything in the scanner, right? When you're not flashing lights or giving somebody pictures and beeps and having them push buttons, what are they doing? Well, they're thinking about their day. They're remembering what they had for lunch. They're worried about getting out of the scanner. So there's things going on. And so from that, we can look at these sort of large scale brain systems. It's a way to map them out in the living brain. Okay. So what getting to the very point of it is if you say, okay, where is that spot deep in the brain, the subgenual 25 that we think is really the culprit, right? This thing is dysregulated. There you've got, too much or not enough of a particular neurotransmitter. And you say, okay, we're going to look at that fluctuating activity in that brain region and say, well, where does it connect up to? Where is its counterpart out here on the cortical surface, right? In this part of the brain that we think of as helping to direct attention. And you can do that. You can say we would call that functional connectivity, meaning that their activity is spontaneously highly correlated. And now if you stimulate this brain region right here on the surface, the right way, for the right number of days in a row, you actually change the activity way deep down in the brain at the target you're trying to hit. And so what they're showing is that, with a week of daily sessions, they're getting effects. Now, these are people typically who, again, have been resistant to multiple medications, 5 or 7 medications. And they're getting benefits on the order of what they were getting with this ECT, possibly better depending on the study and depending on the method. But so it's a big, huge thing for it to have been approved by the FDA. It's now being, now there's psychiatrist labs all over the place buying machines and charging tons of money to go in and sit down and have this done. Sure. But it sounds kind of science fiction-y, but it's real and it's here. And I think it's the cutting edge and the sky's the limit with the kind of things we can do. So
what does this tell us about, to what extent we're just being stimulated by chemicals, right? And magnetic forces, if you will, and we can change people's attitude towards life through depression by impacting them magnetically or chemically. What does that tell us about, the role of the mind versus the role of the brain and free will and the choices we make and the values we make and the relationship between all those things?
It's real softball questions, right?
Yeah, I know.
Well, the way you framed it, it might say, well, actually looks like we are just determined, right? I mean, you shock a bit of the brain here, or you amp up some chemicals in this side or that, and you change who you are, to some degree, yes. But I think what we have to acknowledge is that, the brain and human cognition and our, acting in the world in the ways that we do is an incredibly complex set of processes based on an incredibly complex and integrated set of separate systems.
Yeah.
So, you know, I think that, well, I'll come right out of the closet and say that I'm absolutely a proponent of free will. I believe in volition. And I think that science, I think there's neuroscience probably has lots to say about that.
Yeah.
And it wouldn't be what,
A few minutes, yeah.
pardon me? We'll get there.
Yeah.
But really, I mean, I think that what we have to acknowledge, I'll give an example. You know, I'm sure anybody who drives a car, I'm sure you've had the experience where, you know, you're pretty preoccupied and you're doing a regular old route. You know, so you jump in the car and you've got to get to work and might even be really busy on the streets, you know, your regular commute, and you get there and you jump out and go to grab your bag and realize like, whoa, like
all the time.
Maybe, yeah, what happened? Like you don't even remember driving there.
Yep.
The fact is you may well, you know, the degree to which you were focusing. Now somebody would say, well, do you conclude from that, well, I didn't choose to drive to work.
Yep.
No, I think you know, pretty quickly can say, well, I decided to drive to work and I've automatized so much of that I can get here without really paying attention.
Yep.
No, there's a big, long stretch of time in there where you did all kinds of things. You know, you had to turn the wheel, you had to hit the brakes when the light went red, you had to not run into a car, you know, maybe even had to pull in and get coffee at your drive-through where you always stop. You probably changed your radio station, all those things. And I would say just because you know, may not have been focusing on it that much doesn't mean that you didn't do that or you didn't choose to do all that. There's an incredible importance of the temporal scale of our actions.
Yep.
And so we have, when I talked about these various systems, it's important to bring those up because we know something about them now. And we think that we have, you know, systems of the brain that something we would call the ventral attention system. People argue about lots of things about them, but that actually is sort of like a sentinel, right? It kind of monitors the environment. And if something exceeds that threshold of salience, it you know, bottom up kind of, it takes your attention. So if you're driving and you see, you know, a fire in this, you know, there's a car on fire, it's going to get your attention. But on the other hand, we also have top-down control of our attention, right? So we have a system that allows us to sort of, you know, I think it's probably gating to inhibit the things that are relevant so that we can really focus in and process what matters at the time. And some would say that there's actually a higher level executive control system, and this is something that I've studied and published papers on, that is actually the sort of a higher cognitive system that allows us to switch between these different modes, right? And it's, you know, if I'd say, you know, what is a sort of a key description of what it is to be a human and sort of walk around and survive in the world? Well, you're usually moving about. It's about action. You're doing things.
Yeah.
But typically, you're acting on some sort of short range plan. Like, you know, I want to get out of my seat so I can leave the lecture hall if it's a student, right? But really, it's because you want to leave and get on the subway and go home, right? So that entails being able to draw on your knowledge, right? You have to know what's around you, where you are. You have to have a map in your mind that tells you, when I leave this building, I have to walk this direction to get to the subway. Right? And so a lot of that is introspective. You have to draw on your memory and your knowledge and what you've learned. A lot of it is implicit and just comes up without you noticing it, but a lot of it has to be retrieved intentionally. Like, what am I doing next? Do I have to stop anywhere on the way home? Right? But then you've got to pay attention to what you're doing. You're walking up to the stairs. You got to focus on what you're doing. Yep. Somebody comes up, you have to know when you need to talk to them. So I think that, you know, the nature of a human walking through the world is a constant toggling or connection between your knowledge, your memories, and your goals, your sort of intentions, with your monitoring of the perceptual environment around you. And so, you know, what we think this control system is all about is controlling, toggling your attention or your focus between introspection, or the mind's eye, what you're thinking, and focusing on the world around you.
And how does that relate to Rand's? Because Rand has a unique perspective on free will, as really the initiation of this process of focus, of really, you know, getting your mind in a sense into gear and really focusing on the world out there and being ready to act or to introspect or to be aware of the environment around you. So what you described seems very much fitting to her view of free will, rather than, you know, I think a superficial view of free will is you're literally making a choice in every little thing that you do, which I think is which relates to some of these free will or so-called free will studies that we can talk about in a minute. But hers is really kind of a master control, right?
Yeah, I mean, in a sense, you know, I would start by absolutely agreeing with you. I think that she has to my knowledge, and I'm not a philosopher, but I've studied philosophy and Ayn Rand's philosophy, has a radically different view of free will, where she is a champion of free will. It believes has a very particular understanding and definition of what volition entails and what it means to have free will and how that actually plays out. And so I guess the way I would start is by contrasting that with what I think people are kind of caught in this dichotomy where either the scientific one, right? So what do we know from science? Well, that things are causal, they're determined. The world is orderly, things act in a certain way and they only act in that way. We may not know, we may not be omniscient, but what we do know is that things, act in a particular way. And so the human brain, the human and the human mind and the human brain is nothing special in that respect. It's made up of the same matter and the same stuff as other, inanimate things and other animals.
Yep.
And so why would that be any different? At some level, all of these things are acting under the same principles and they're determined, and we know that there's causality, right? And that the only alternative to that is, well, no, we know we choose our actions and we're responsible for our actions. And I think that the only answer to that is, there isn't enough of a scientific answer to that. Is that it's mystical, right? And there are different variants. There's indeterminism, there are compatibilism, there are different ideas one could get into, but really to me, it's been a dichotomy. It's either something mystical and we believe it on faith and it's subjective. We know it because we feel it, right? It's a subjective sense, and you decide to deal with that, or you decide to face the facts of science and realize that we're determined.
Yep.
And I would, potentially, hopefully not offending any of my contemporary colleagues, would say that the vast majority, well, I would absolutely argue the vast majority, if not most or almost all, neuroscientists would be determinists. I don't know, now it's not all of them, but I don't know of many people who believe that we have free will in the way that we mean or think it, or at least don't have much of an explanation. And so what I think is radically important and interesting about Ayn Rand's idea is that it's really fundamental and simple in a sense, in that it's the choice to focus or not, right? To engage one's ability to control their thoughts. Now, I think the sort of the false straw man is the idea that, well, there's all kinds of stuff going on that you're not aware of, So the same argument I just used about the car, right? Where you can drive here. You could find that almost a variant of that same example in a book by Sam Harris, for example, who would say, you didn't choose any of these things. I'm just here at any given moment, something's going on. I have a sense that I wanted to be here, but I can't say why this happened or that. And there's always a chain of random things that I can't explain that brought me to thinking this or doing that.
And we just ex post explain these things to justify them to ourselves, but they,
well, it's epiphenomenal, right? It's this idea that, somehow, which I've never understood, it doesn't make sense why that would be or how it would come about. But it's that false dichotomy that, well, you can't explain all of these things. So how can you say you have control? Well, that's not where free will or volition is taking place, right? It's explicitly where it isn't. And we wouldn't get very far if we had to control every little movement of every muscle, even to just do something like this. Sure. It's incredibly complicated. We have programs that when I say I want to roll my fist in an orderly fashion like that, I don't have to think about it after that. I just tell myself to do it. But that doesn't mean that I don't have control of my finger or my finger is moving because of something else. So the point, I think, is that free will starts at a much earlier, much more fundamental stage. And Ayn Rand pointed that out. And it was really the fundamental choice to focus or not. And by focus, that means to, engage your rational faculty and either pay attention to what the contents of your mind or pay attention to the contents of the world around you, and choose from there. So,
has there been any of these kind of imaging about in trying to see if you can identify that the focal point of focus in a sense of? Especially with my colleague Nathan Spring, when he started this stuff at Harvard, we were really interested in sort of volitional, goal-oriented planning. And I would say that I got involved with that enterprise from the neuroscience and understanding the brain networks. But my good friend and colleague Nathan Spring really pushed this field. And this is about trying to understand, okay, it actually is an interesting story if one has time to delve into it, but there was we discovered this mysterious network in the brain, right? That everybody thought was, something that when we gave people a task, we gave them something to do, this thing turned off, right? So people didn't notice it for a long time. It started in PET scans. We'd always say, okay,
put you in a PET scanner and we can say, what does your brain look like when you're reading or thinking or remembering? But if people started to realize, wow, if you actually look at our little baseline runs where you said, just close your eyes or just rest, don't do anything. Lo and behold, over all these studies, there's this core similar set of regions that always seems to become really active, right? Well, again, of course, cognitive neuroscience centric, people aren't doing nothing. They're engaging in probably a lot of introspection, mind wandering. Yep. There's a lot to be said here. And this is something called the default network. And this thing kind of took the field by storm too and has been studied. We now know that, and people I think refer to it as a task negative network. It was when you sort of go out of focus, when you let go, when you mind wander, and you just do random association or float, you default to this, and it's the default network. Okay. Well, in fact, we don't think what our research shows and what we argue is that it's nothing like that. It actually plays an extremely important role because you see that this thing becomes highly engaged, highly connected, and will connect with this higher control system I was talking about when you're introspecting. Some people would argue that it has to do with processing about oneself, or some people would say, originally thought they called it a mental time travel network, when you're remembering the past or projecting into the future. Or maybe it's anytime you're projecting your mind away from the here and now, the perceptual environment around you. We argued that it's, and I hold, and I wouldn't speak for even my colleagues now, but that this is the system that's critical for introspection, which is, I think, at a conscious level, a uniquely human conceptual capability. And so that's been an interesting development. And the idea being here that that's the kind of, when you ask, has anybody looked at this? Well, we tried to understand, we've got this network that people thought turns off when you're engaged. It's not goal directed, but it is. What is the nature of that? Well, when you're introspecting, or at least projecting away from my perceptual environment, when you engage somebody in a task that requires them to focus either visually, auditorily, or in their system, you've got a completely different system. It's kind of a yin yang, these anti-correlated systems. When one's on, the other's off, and they switch and they go back and forth. Interesting. What we found is that right in the middle of them, literally anatomically interposed, is what we refer to as this frontoparietal control network. And when people are engaged in purposeful introspection, this executive control system is coupled or functionally sort of linked with this default or internal system. And when they switch and focus on the external world, it lets go of that and couples with the other system. And so we think, this is sort of getting there. It doesn't get down to the philosophical or metaphysical or, epistemological explanations of free will or cognitive control, but I think we're starting to get an idea of how it works.
Okay. Interesting. So let's talk a little bit about Sam Harris's claim that neuroscience proves that there's no such thing as free will. And I think he cites kind of these famous experiments that were done. So why don't you take us through that and tell us what's wrong with those claims? Sure.
Yeah. So I have it here. Actually, I've read this. This is right. Sam Harris has this book that he did called Free Will. Yep. And of course, the picture has marionette strings because the implication is that we don't have free will. Yep. And it's a short book. It's pretty to the point, but I think in terms of what neuroscience has to say, he says what a lot of neuroscientists would say, and a lot of people say, is that, well, neuroscience has already shown us that we don't have free will, right? It's done. We know that. Yep. And also, why would you think we do? We're physical beings, and we know that physical matter is just the other thing I said. And so there are some famous, I would say, infamous studies. Earliest one, I think late 60s, don't quote me on the year, by a guy named Libet, or some people say Libet, but it's Libet, Benjamin Libet. And he did these sort of seminal experiments where he studied what he was calling, volition or free will. And they're striking, they're interesting. If somebody just describes the experiment to you, you can say, damn, wow, how does that work? Maybe you don't have free will. And I'm going to tell you about that and about some more modern studies that are even more challenging. Right? Yep. The basic idea was this, and there were variants of the experiment, but I actually have a nice little graphic of it, but I'm not going to try and screen share. The idea is that you just bring somebody into a lab and using a really simple brain imaging technique called EEG or electroencephalography. That's really just putting some electrodes on the scalp, and these things pick up electrical activity that is related to brain, like waves, it's waves of neural activity. So the cortical activity under the skull will give off particular kinds of patterns of electrical activity that you can read on the surface with these electrodes, EEG. And so you put an EEG cap on someone and sit them down and say, okay, I've got a clock over here with an arm that's turning around, or something like a clock. It's a dial with an arrow. It's turning. And all I want you to do is every once in a while, at a time of your own choosing, for whatever reason, just tap your finger or move your finger or push a button. And say, in fact, and most of these experiments are instructed explicitly not to come up with a reason or a strategy. Just, don't try to. Just whenever the urge should strike, or at some point, just tap your finger. But here's the kicker, though. We want you to watch this clock. And you want you to really keep your eyes on that thing and see where it is. And the moment that you make that decision, the moment that you have that urge and you're about to hit your finger, mark what time the clock is at, right? And so what they would do this a bunch of times. They would do it as many times as the person chose to tap their finger. Sure. And then what the cool thing is, they would say, okay, they could now go for every time that person tapped their finger, they could go back and say where the clock was at, the person reported. And they would report, the time as being just before they tapped their finger.
Yep. Neural
What the kicker here is that they would then look at the brain activity, and there was averaging over a bunch of these trials, they would see a neural signature or an electrical pattern at some point before, not just the finger tap, but before the person indicated they had their initial urge to move their finger.
Yep. Right.
So, and this called I blank on the name of it, the positive potential. So, right. So they'd see this buildup of electrical activity. They would get to a certain point, and lo and behold, the person would say the time was X. That's when they decided. And then some number of milliseconds later, they'd tap the button. And so people have used this to say, look, the brain has decided when to tap, right? You didn't know you were going to move your finger at that point. And we can see some brain activity here. And then you decided to tap and you tapped. So clearly, the brain is doing whatever it's doing. There's probably causal things happening. Something happened. And then after the fact, you interpreted that as your choice, right? But it was, you didn't choose it. The brain had already made its decision, right? Not your conscious awareness, the brain decided, or, some causal thing happened. And so I think people struggle to explain that. Now, there's a lot of other interesting nuances here where Libet also said, it actually turns out, though, that you also have the power to stop. So you don't have the power to choose, but you have the power to stop the choice. Because if you tell them, decide when you do that, but sometimes withhold, people could do that, right? So there's a lot to be said. And I think there are all kinds of arguments. And I'm going to focus on what I think is really fundamentally wrong with it. Yep. But I will point out that there's some good stuff that's been written on this. In fact, a very recent review article just came out where they looked at the Libet studies and all the studies sort of its ilk since, and reviewed it and said, what is really the impact and what have they shown? But a very good book, a recent book came out by a guy named Ed Locke, who is a longtime mentor of mine. And we all know Ed. Yep. Ed Locke wrote a book on free will, and he has a chapter devoted to sort of debunking the Libet studies. I think he does a good job. But here I just will add by saying some of the arguments were, well, how do you break down, it's a process. It's going to unfold over time, right? We're talking within a couple of milliseconds. At some stage, you have to, some kind of a mental process builds up where you decide you've hit threshold and you're going to tap the button. And maybe what we're seeing is just the build up to that. Or, there's been all kinds of those kinds of arguments, or has something to do with the timing. People aren't very good at picking the dial, they've already decided by the time they can pick up the time. But some of that is a distraction, right? Because another study came out not too long ago, where they did the similar kind of thing with functional MRI. Now, I mentioned earlier that we've got these sort of multivoxel pattern analyses, or these advanced techniques. Well, now they did almost the exact same experiment. They show people images, they get people to indicate when they've made some kind of a choice, and then they do the choice. And they're able to decode from the brain activity up to 10 seconds earlier. Not 100%, but better than chance what that person's going to do. So they're saying, look, it's not about, we're looking 10 seconds before. If you're telling us that, it's a 10-second process to volitionally come up with a quick urge to tap your finger, then so how do you answer that, right? Well, I think that right off the bat, any of these experiments aren't a properly designed complete experiment, right? So I've tried to demonstrate this in the past, but the one thing you would have to do is have these same people in the same period of time and not give them the instruction to decide to move their finger and see if any finger movements happen. I think one thing is to step back and say, we're on a very different temporal scale here, right? Everybody in this experiment was told to, I want you to set the goal right now. You're going to enact some sort of a sustained cognitive state that's going to result in you tapping your finger every so often for the next 2 minutes. But when I tell you it's over, you're probably not going to keep tapping your finger. And the odds are you weren't tapping your finger before you came in here, right? So it begs the whole question, or skips the whole point, that there was an instruction that resulted in. So, something was set in motion at that moment when, this gets back to the idea of when did you decide to operate your car? Well, when you jumped in it and enacted a motor program, right? Now, one thing that Ed Locke points out really well, and others have, and I would, is that this is not free will at all. The idea of, intentionally for no reason, flick your finger or let it flick.
Yes.
Is kind of, in a sense, the antithesis of what it means to focus on something and do, actually choose to do something.
Well, there's a key word, I think, when they talk about these experiments, there's a key word that suggests that, and that is urge.
The urge, yeah.
Talk about the urge to tap your finger. But, where's the choice? The urge is, where does the urge come from? It's just a biological urge or cognitive or whatever. It's driven. But it's an urge. It's not a choice.
Yeah. Now, this is actually something I mentioned to you before, Your Honor, that I would like to look into more, review more, study a little bit, and write a little more on, because, and it's beyond the scope of the discussion here today, but there's an incredible sort of accumulation of really interesting neuroscience findings showing that, yes, different things going on, different phenomena going on in the brain that seem to be some of these fluctuations have an effect on the output of our behavior, out of our awareness. And some of it may be beyond, be really beyond our control. I was talking about those randomly fluctuating patterns of activity before. Well, somebody showed that if you just have people making a motor movement with their finger, that if they happen to do that at the moment when those random fluctuation peaks are high, they actually make the motion with quite a bit more force than if it's low, right? So, this is to say that, once again, of course, there are all kinds of forces acting on us and that contribute to our behavior. Lots of them are implicit, maybe most of them, part of what I studied for a lot of the 5 years when I was at Harvard, and even since then, was something called implicit memory. And that is all the processes and the way you can look at the brain and see things going on that are outside of our awareness, but that yet have a pretty significant impact on our behavior.
Yep.
None of that negates the idea that you still have control. So the real way to do that experiment would be to bring in, two groups of people, instruct one to, sit down with this setup, and whenever they have an urge, move their finger, and tell the other group to sit there and, not move their finger or do something else. And what you'll find is that instruction, and I guarantee you that there will be differences in the brain activity at the outset that are going to predict whether or not which group they're in, so, and it might be that,
that you're not, whatever you're testing there, you're still not testing free will, because free will is not what's involved in the urge to, or the commitment to the instruction of pressing the button. Just like I don't think there's much free will engaged in driving to work. As you said, it's the decision to drive to work. It's the getting up in the morning and focusing on, yes, I need to go to work today, where the free will is engaged. But once you get in that car and you're driving, unless something unusual happens, and even then it's so fast, you're not engaging free will. There's little, of that. You're in focus. You're in focus enough to drive, but you're actually, in the old days when we used to shift gears, I don't know if you ever drove a car with a gear shift. Yep. It's amazing how you shift those gears without thinking. Literally, you're shifting those gears without giving it another thought, and it's automatized. And you can't say, well, yes, that proves there's no free will because he did it automatically.
That's right. Yeah, it's absurd. To me, it's absurd on the face of it. It isn't, obviously, but if you just compare that to try and actually remember, use your episodic memory, your human episodic memory, and think of those first times when you're trying to learn to drive.
Oh yeah,
it's extremely demanding. You'd be exhausted after. You can't do it all at once, right?
Yeah, so you couldn't shift the gear and do anything else and look at the street. You had to focus on, and that's where you really engaged.
Yeah,
your mind is. But once you automatized it, that engagement gone. And tapping a finger or clutching a fist or whatever it is that they were doing requires no focus, no effort, no exercise of will in the sense that we mean will.
in the sense that in the objectives, or what Ayn Rand called, the locus of our free will or of volition, it's complete. It's really not that. It's about anything but. Now, I think I think it's really interesting. What the hell is going on there? What is that urge?
Yes.
Why does it look similar? But I mean, even to say, well, does that kind of a pattern happen in the brains of people, but they're not flicking their finger? I mean, there's all kinds of questions, but it's interesting that those haven't been chased down. And in almost any other kind of experiment, those would be things that would be required. I mean, these are basic elements of a properly designed experimental study.
Sure. You want a control group.
Yeah. So I thought about running that. It almost seems like a waste of money though, because I know what's going to happen if I get a group of people, sit them down there and don't tell them anything about moving their finger, But
Well, I mean, it would just be, given how influential these studies seem to be, anything done to debunk them seems to have some value. Maybe not.
I think so. No, I think and I do have to credit my favorite quote about this, and I'm not sure the original source, but I credit it to a guy named Lee Pearson. He calls it not free will, but free whim.
Yeah.
I think that's pretty good. Studies on free whim.
Yep. Good. So I've got a whole list of things we can still talk about, but we're already at an hour and a half.
Okay.
Let me, so I have some random questions.
Any good
I
ones?
don't even know. I don't know. I mean, random questions that people are paid money to ask. So
Okay.
I'm obligated to ask you because of that.
I'm happy to answer if I can.
Yeah, I don't know what you'll think of these, but what is your guest view on déjà vu?
Oh, déjà vu. Yeah. Déjà vu is an incredibly interesting phenomenon.
Oh, it is. Okay.
Yeah. I love that. I'm going to one up that and say, how about the idea of the tip of the tongue? Right. I'll talk about déjà vu, but.
Well, the tip of the tongue, I'm curious about, because that I have a lot. Déjà vu, I don't have that often, but tip of the tongue.
Probably what motivated me to go into memory research, but I'll talk about déjà vu. And I mean, we have theories about what does that. I think it's an interesting phenomenon, and it can be pathological. There are people who have that. There's a disorder where people have running déjà vu, like either a lot or constantly, and you can imagine what that would be like. I think the best explanation that I've heard of that, and again, I'm not an expert in this particular topic, but I know something about the brain systems that are involved, is that typically, as we sort of navigate around the world, again, this relates back to memory. You see things you recognize, and a lot of the memories or the reenactments of knowledge and experiences we know happen very implicitly without our awareness. And so you're walking down the street and you see a familiar face, right? And but that's an automatic. It's a sense of familiarity. Mm-hmm. And the classic example is they say the butcher on the bus syndrome, where you see somebody, you're like, I know them, and they're smiling at you, and you know they know you, and you're supposed to know them, and they're walking up, and you're thinking, God, I don't know who that is, right? And then maybe they say hi, and that you remember, or maybe you say hi, and you walk by, and then afterwards, like, oh my God, that was, it's because they're in a different context, right? So you're used to seeing your butcher in the butcher shop, you see him there, but when you see him out of that context, you might recognize him, but you can't. That's the difference between this sort of implicit memory and the episodic, bringing the actual associations back into conscious awareness. But that feeling of familiarity, as we know quite a bit about the neural circuitry that sends up that signal. And so I think the theory here is that you're encountering somebody, you're in a mode where you're encountering something new, which is the current moment, but something has initiated or sparked a familiarity signal.
Okay.
So it's kind of like a mismatch. You've got this familiarity coming up, telling you, oh, I know them, or this feels like I've had this. So you get the sense that you must have dreamed it. And sometimes you feel like you almost might predict what's going up. Now, if somebody tells you that, no, I could feel it, and I actually knew what they were going to say, and they said it, I don't believe that happens. It would be a real fluke, or it would be some kind of ESP that I've never seen. Yep. But people have the sense they could, but if you actually try to get somebody to do it, they probably can't. So it's a sense, it's a false sense of familiarity that it's like a signal that turns on and gives you the sense that what you're doing is familiar, and so you think you've been there before. Yeah. There's some other really interesting disorders, actually, bizarre neurological disorders that happen from particular kinds of brain damage that are related to sort of the reverse of that.
Okay, interesting.
Which I won't get into unless somebody asks.
So you are also going to connect to the tip of the tongue.
Yeah, tip of the tongue. So what blows my mind is this. So the example I give is always a music one. So I can be driving and a song comes on the radio. I'm like, oh, I like that song, and then it ends. Like, I wanted to remember the name of the band, right? Or the artist or the singer or the composer. And I know it, right? I know it. I'm ashamed of myself because I know it so well, but I just can't get the name. And then you get that feeling where it's fleeting by, right? You might go, maybe it starts with an S, or it sounds like something, and it's sort of waving by your consciousness, but you can't grab it, Yeah. Well, what blows me away is that how can you be sitting there and possibly know with high confidence that you know something, but you currently don't know it?
Yeah.
That tells you there's a whole lot of interesting stuff going on. And I know we know something about the neural circuitry. And again, Dan Schachter, I worked for, published a paper on this, the tip of the tongue phenomenon.
Yep.
But the idea that, and people have studied it, what's quite interesting is that when people say, when they have those, you can sort of induce that situation in a laboratory environment. And what you can ask is people, how confident are you, like if you can't remember this, but how confident are you that you remember it if I show you a list or I tell you the name? And they can say 100%. And people are quite good at knowing how well they know it.
Yeah.
It's an interesting phenomenon. Like, where is that information in the brain?
Yeah.
Anyway.
They know it's there, but they can't access it somehow. But how do they know it's there if they can't access it? So
It's interesting.
It is interesting. Okay.
You know it implicitly.
There's a lot more to these questions than I thought. Okay, here's another one. I have no idea what this even means. But have you heard of the method of loci? Is it BS? Loci, LOCI.
The method of loci. I don't know what that's referring to. Okay. If it specifically has to do with the method, I would probably need more information. If we talk about, I know I have lots to say about localization and the value and means of localizing brain activity, but I don't know if that would be it. And I apologize, I don't know.
What do you think of hypnosis?
Hypnosis?
Yeah.
Again, not an expert. I got really interested in that partway through my undergrad, and I got to participate in some experiments where I was presumably, to be hypnotized, and it had some kind of interesting effects. I will start by saying I don't think that it's just a big ruse, that it's bunk. That every time you would go to, say, a hypnotist show and people are up there acting, that they're just completely play acting or going along. There's definitely something going on there. But is it like, the way it's presented is in a magical kind of way that really, this person is gone to some kind of, they've disconnected with reality and they're experiencing another reality. And I don't think it's like that either. And if you talk to people who've gone through hypnosis, they often don't describe it as such. I think it does have to do with reflect the power of the mind to focus really intently on something, and to the point that you can, in a safe environment, sort of temporarily suspend, a reference to something else or a reference to disbelief. There's a guy named Dr. Rausch who was the father of a friend of mine back in the 80s, when I grew up in the 80s, and who was on a show called That's Incredible. And this guy was on that show because he hypnotized himself and he's a dentist or dental surgeon. He did work on his own mouth by self-hypnotizing. And what exactly that means, mind over matter, I don't know a ton about it. There's a lot written on it, but there's, if you mean what do I think about it in terms of a treatment? All kinds of people use hypnosis in treatment or to treat different disorders. I don't know. I think that there's some evidence that there might be some efficacy, but that might be not, unlike, some other different sort of mindfulness practice techniques or some meditation, changing your focus. Or I think Jeannie even brought up the idea of a desensitization theory for phobias. I'm not an expert on it, but and I don't really know.
Okay. All right. So we're going to have you back because I still want to talk to you about your views on psychology as a science.
Yeah.
And then there was the replication crisis we said we talk about, but we'll have to do some other time because we've gone an hour and a half just like that.
Yeah, time flies. I thought it was going to be long, but it's not long.
No.
And I didn't really get to dig in and talk about the core thing that I'm interested in. That's the concepts. What do we mean?
Yeah. So why don't you say something about that? So at least tease that in a sense of, okay, so you're interested in concepts. What is neuroscience and concepts? What is it that you're studying there?
Okay, well, I'll give one. I'll just give one neat example. And I like to go to this one because it's one of these ones where there's kind of a raging battle. There are two sides, and there's a big battle going on in the field that other people may not know about. But in the field, it's a pretty big battle. Yeah. And it's between the people who, on one extreme, you have this idea where it's concepts. It's a distributed representation model versus people who believe in a semantic hub. So what do I mean by that?
Okay.
One is that, and some of this really gets down to sort of the epistemological or philosophical nature of what a concept is. again, most of the people studying couldn't define concept or don't know what it means. But if we stick to something like, first level concepts, we know what a chair is.
Yep.
A chair is that, it's that, it's that. There are lots of them, but I can call all these things chair without getting into the nature of a concept. There's some really cool stuff where I think people for a long time coming from the neuropsychology literature would argue that people who had damage to this anterior temporal lobe, so this is the temple, right? Temporal lobe is part of the brain that sits here. That's my brain model. There's a brain looking at you.
Yeah.
Right?
Cool.
Way up here, the temporal pole.
Yeah.
People have sort of said, people get something called frontotemporal dementia or semantic dementia. And rather than losing their ability to remember where they put their keys or how to get from point A to point B or what they had for lunch, they start losing their semantics, which is the thing I was thinking, like their facts, their knowledge. Often people think of it as verbal. They start losing the names for things.
Yep.
So the classic example is a man driving in the country. They're going from their home to a cottage they've been to, and he's driving and making all the turns to get there and looks into the field and points out and says, "What are those things?" And his wife says, "Well, those are sheep, and they live in Ireland." Of course, he knows what sheep are, but he's lost. Yep. He might say there's creatures,
Yep.
and this progressively happens. And they would argue that the disorder afflicts here. And so in order to have concepts, you have to have some sort of an amodal hub in the brain where these concepts are stored, right? Because, for example, the concept hammer, if you hear the clinking of a hammer, you can think of it. If you read the word HAMMER, if you see a picture of a hammer, they all relate in some way. Yeah. So there must be some amodal, some sort of amodal representation of that in the brain. And it's probably up here in the anterior temporal lobes. The flip side of that is that, and some of this work is amazing stuff pioneered by my former advisor, Alex Martin, showing that actually activation of a concept looks more like a weighted reactivation of the brain regions that are critical for processing the essential characteristics of the concept. So okay. What do I mean? I'll try to get through that quickly. Here, I'm going to use my brain model again. Yeah. We know lots about what different brain regions do in terms of their process, right? So we know vision happens here. Information comes from the eyes, goes to the back of the brain here, and then travels down in the ventral stream down here and up into dorsal stream. Well, what we think about this dorsal visual stream, and it may not be only visual, it's an action stream, right? So it's about knowing where things are, your body, and where things are in space in relation to you and your surroundings, and being able to act on the environment. So to reach out and grab a water bottle is incredibly complex calculation. We do it without even thinking about it, right? So that stream is responsible for that. We know that there's a region in the brain that's critical for storing, or people say storing or representing motor programs, like to grab or grasp something. And there's another region that we know is critical for understanding like mechanical motion, movement of things that is not articulated like living things. So the idea here is that when you see a tool, for example, now a tool can look like about anything. A hammer, if a tool is something that you use where its form is related to its function, you can think of a hammer, a screwdriver, a basketball, maybe not a basketball, but a tennis racket, a Q-tip. Yep. For some reason, there's an interesting thing where as soon as almost the second you show somebody a stimulus that there's a tool and they recognize it as a tool, you get, again, I'll use the term light up again, but you get activation of brain regions almost automatically, obligatorily, that look just like if somebody were about to use a tool. So if I show you something and it's a hammer, and I look at the brain, I look at brain activity compared to them looking at something else. Yeah. You see this reaching, grasping, motor program, motion circuit. Almost like if I were to reach out and grab and use a hammer.
Well, even though you're not doing that, of course.
No, the sound of a hammer, the word hammer, and it happens faster than you could, actually do anything. Sure. And so the idea here is that you're reactivating brain regions that are critical for those, for a tool. It's pretty easy to say, what are the essential properties of the concept tool, right? Well, it's movement, it's how you interact with it and how you would, use it for a manual tool. Yeah. Whereas if I show you an animal, right? And an animal can look like an ant, a worm, an elephant, a giraffe, a hawk, an octopus, right? Well, there's a very consistent set of brain regions that are radically different from what you see when you look at a tool. And it's going to be things like a brain region called the amygdala, which is for emotion, like associations of, fear, reward, it's food, it's an enemy, right? A region of the brain that processes faces or body parts, So these are sort of contrasting views. You've got distributed representation of concepts. Now that's interesting. That connects to me in a really basic, maybe superficial way to the idea of the objectivist idea of concepts, and that a concept is not in and of itself something. It's just kind of an, at the end of it, it's a word that is an intentionally abstract thing, but it's like a file folder, right? This is the file folder analogy, and Harry Binswanger's done incredible work on this. But ultimately, if you delve into that or you enact it, it's going to be, it's nothing more than a bunch of concretes that go in that folder. So, I mean, that's
Part of those concretes are what like the actions that you take with the tool are some of the things in that file folder, and the brain is in a sense accessing that.
that's the idea. And that, you know, again, this is, you know, a lot of other people have done this work and there's lots of evidence, but my thinking of it this way is kind of new. I'm still working through how that works.
Okay.
And it's a new way of framing it, but that's one little taste. There's a lot more to it than that. It gets into the idea of, do we, you know, these brains, again, the idea that I said, these brains are so similar across individuals that we can read one person's brain from another person's activity, you know, or what one person is thinking, telling a story by looking at another person's brain, watching the same movie, or, you know, I can, you know, grab anybody's brain and point to within a millimeter, the part of the brain that's going to sort of become the most active when they see a face, relative to seeing an animal or something else.
Yeah.
So how could that be? Well, people would argue, well, these are critical things that over evolution, we've evolved modules for these kinds of content. Yeah. And I would say absolutely not. We have processes and we have systems that are designed to achieve certain things, but it's that we definitely have an identity. We have a circuit board, but that interacts with the world in a particular way. And you have to have that experience to build up those representations. So that's, you know, sort of the way I think of that is the idea of objectivity playing out in our brain and the way we learn. But there's a lot more to say on all that.
Yeah. Good. Well, we'll have to have you back and talk more about that and talk about some of these other issues. Great. Well, thanks, Dale. Really.
Thank you, Yaron. It was fun.
Good. All the best with the research. It's truly fascinating.
Well, thanks. Thanks. I dig it.
Good. I can tell.
Yeah.
Excellent. Thanks, guys. Remind everybody, if you like these interviews, then help make them happen. Support the show on Patreon, subscribe to the YouTube channel, and of course, most importantly, share the video. Let people know that you liked it by sharing it. Great. I will probably do, next show is probably next Saturday. I'm taking a few days off, going to Vegas. That'll be interesting. To relax a little bit, and we'll be back probably on Saturday. Thanks, Dale.
Enjoy. Thanks, Yaron.
Thanks. Bye. Bye, everybody.
Bye, everybody.